We live at the bottom of a heavy ocean. For 200,000 years, humanity looked up at this ocean of air and saw only a barrier. It was the domain of gods, of birds, of dreams that woke you up in a cold sweat. The atmosphere is not empty space. It is a physical substance. It has weight, it has viscosity. It fights anything that tries to move through it. To conquer this ocean, we didn't just need wings. We needed a heart. We needed a machine capable of inhaling a thunderstorm and spitting out a hurricane. We needed the gas turbine engine. The evolution from the piston engine to the jet engine is not just an improvement, it is a transformation of species. It is the difference between crawling and teleportation. Today, the high-bypass turbofan engine is the single most efficient, power-dense, and reliable transportation machine ever conceived by the human mind. It is a device composed of over 30,000 individual parts. It operates at temperatures that exceed the melting point of its own components. It spins at speeds that create centrifugal forces 10,000 times the force of gravity. And it does this while flying 600 miles per hour at 40,000 feet for 14 hours straight without a single stutter. How? How do we take rocks from the ground, bauxite, rutile, ilmenite, and turn them into a machine that defies physics? The answer is a story of extreme manufacturing, a story of tolerances measured in microns and forces measured in tons, so you can understand the miracle of flight. This is the anatomy of a Titan. The fan, forging the shield. We begin at the front, the cold section, the fan. If you look at a modern airliner, the engine looks huge. That is because of the bypass ratio. In a high bypass engine, 90% of the air never even touches the fire. It is pushed around the core by this massive fan, acting like a giant ducted propeller. To move that much air, the fan blades must be enormous, often over 4 feet long. They must be incredibly light to spin, but incredibly strong to survive. The material of choice is titanium, specifically an alloy called Ti6Al4 Vi, titanium, aluminum, and vanadium. But here is the problem. A solid titanium blade of this size would weigh too much. It would act as a massive flywheel, making the engine sluggish and heavy. The solution is one of the most guarded secrets in aerospace manufacturing: the hollow blade. Engineers take 3 sheets of titanium. They paint a stop-off pattern on the middle sheet, a chemical that prevents welding. They stack the sheets and heat them in a vacuum furnace until they bond at the atomic level, becoming a single block of metal everywhere except where the paint is. Then, while the metal is glowing red-hot and soft, a state called superplasticity, they inject inert argon gas between the sheets. The gas pressure forces the metal to balloon outward, filling the mold. The internal sheet stretches into a honeycomb truss structure, creating a blade that is mostly air on the inside, but rigid as steel on the outside. The leading edge of this blade will slice through the air at supersonic speeds, even when the plane is sitting on the runway. Because the tips of the fan blades travel faster than the speed of sound, they are coated in titanium nitride, or high-strength steel sheaths, to prevent erosion from rain and dust. The compressor, the great squeeze. By the time the air leaves the compressor, it is already 600 degrees Celsius. It is a dense, hot, energetic gas. It is ready for the fire. This is the combustor. The job of the combustor is to mix fuel with this high-pressure air and burn it. But it's not just burning, it is keeping a flame lit in a hurricane. The air is moving through this section at hundreds of feet per second. If the flame blows out, a flameout, the engine stops. The fuel nozzles are marvels of 3D printing, additive manufacturing. In engines like the GELEAP, the fuel nozzle is printed as a single piece, replacing 20 different welded parts. This allows for complex internal geometries that swirl the fuel and air into a perfect atomized mist for maximum efficiency. But here's the paradox. The temperature of the burning jet fuel reaches 2,200 degrees Celsius. The melting point of the metal alloy used to build the combustor is roughly 1,400 degrees Celsius. The fire is hotter than the container. The solution is film cooling. The walls of the combustion chamber are drilled with thousands of microscopic laser holes. A layer of cool air from the compressor is forced through these holes, creating a thin, protective blanket of air that hugs the metal. The flame never actually touches the wall. It floats inside a cage of air. The turbine, the crystal heart. Directly downstream of this inferno lies the high-pressure turbine. This is the most hostile environment in any mechanical system on Earth. These blades are responsible for extracting the energy from the fire to drive the compressor and the fan. Each one of these blades, smaller than your forearm, extracts roughly 800 horsepower from the gas stream. That is the power of a Formula One car in a single blade, and there are dozens of them. Normal metal is made of grains, tiny crystals jumbled together. At high temperatures and extreme centrifugal loads, the boundaries between these grains become slippery. The metal creates microscopic cracks and creeps. It stretches like taffy. This leads to failure. To solve this, engineers decided to eliminate the grains entirely. Using a process called single crystal investment casting, the metal is poured into a mold with a pigtail selector at the bottom. As the metal solidifies, the corkscrew shape filters out all the crystals except one. The entire blade grows as one single continuous crystal lattice. There are no grain boundaries. There are no weak points. It is effectively a metallic gem, but even a single crystal of superalloy will melt at 2,200 degrees. So the blade is coated in a thermal barrier coating, TBC, a ceramic layer of yttria-stabilized zirconia. This ceramic acts like a heat shield, insulating the metal from the direct blast of the fire. And finally, the blade is hollow. Cool air from the compressor is pumped inside the turbine blade, circulating through a labyrinth of serpentine passages to cool the metal from the inside out. It then exits through tiny holes on the blade surface to add to the film cooling. It is a radiator, a heat shield, and a power plant, all in one. Intermission. The complexity of scale. We have only described the major organs. We haven't touched the nervous system, the miles of wiring. We haven't touched the skeleton, the titanium and steel casings that hold this bomb in check. A Boeing 777 engine weighs over 18,000 pounds. It costs upwards of $30 million. It is an investment in physics, and we are only halfway through the build.